Hello everyone, and thank you for giving me the chance to join the RISC V Summit this year. My name is Leon Tien. I am a PhD student from the University of Electrocommunication, USC in Tokyo, Japan. My talk today will about the Spectre on a hybrid multi-core RISC V. Our work is from the collaboration between the university, the ASIS and the Chancellor. This present work is also supported by the new Engineering and Industrial Technology Development Organization, NATO. In this presentation, I will talk about the first two well-known variants of the spectral attack, as we could also name the cut side channel attack. We also implement some straightforward software-based mitigation method to prevent the issue of cut side channel attack. All of the experiments would be implemented and executed on a RISC V hybrid processor, which contains an in-order processor and an out-order core. Now we will go to the introduction. The focus of our team is about develop and examine the RISC V-based processor along with many open source projects in the RISC V ecosystem. And security is one of the interesting domains. With multiple types of side channel attack on the cut have been discovered, especially the Spectre. The RISC V provides a very suitable environment to experiment and examine them. There are research about Spectre on Boom, so extending with the research, we also want to examine the Spectre on a multi-core system that contains an in-order core and an out-order core. So, in 2018, Spectre and Meltdown have been discovered as two serious security flaws in modern computer processors. They both could achieve private information which could currently be processed on the memory of the chip. On the one hand, the Meltdown exploits the out-order execution in the Intel processor. On the other hand, the Spectre takes advantage of the speculative execution mechanism of many modern processors, so that it could trick the victim application into giving up the private information. Normally, the information is in the cache of the system. This security hole has become an interesting subject to study. So, in the RISC V ecosystem, the University of Berkeley has developed an out-order RISC V processor that called Boom. The Boom architecture contains some fundamentals which provide a very simple environment for spectral attack. First, the speculative execution has been implemented to optimize the computer system, along with other parts could be exploited, such as the brand credit unit, the brand history buffer, or the cache. So, extending with the research, the RISC V ecosystem also has an in-order core called Rocket. Both of them, the Rocket and the Boom, have their advantage and disadvantage. Accordingly, we are now continue to experiment the Spectre on a multi-core processor. This hybrid processor would combine and enhance the distinct advantage of the out-order and the in-order processor. Therefore, it becomes a good target for this security experiment. Now we will come to the second part. We'll talk about the Spectre on the cache attack. So the core technique of the first two variants of the Spectre attack is called flush and reload. The flush and reload technique is performed based on the observing the side effect of the processor memory when executing the program. There is a huge difference in speed when the data needed by CPU is already fed in cache, which we normally call cache hit, which when the CPU had to go to the memory to achieve the information. First, the attacker would flush the share address in the memory cache, which in the Boom core we choose the L1 cache. Then the attacker will wait for the victim function to access the private information. Finally, the attacker will reload to the array to find out which element within time is faster than other. So therefore, it will be the earlier asset element, which will be a character in the private string. So they can repeatedly do it and achieve the full string. So in this work, we will focus on the first two well-known variants of the Spectre attack. The first one is a budget bypass. So in the attack, the conditional brand becomes the target. Typically, the conditional brand would be executed in the sequential order. The inside code block would only be executed after the conditional is smaller than a size ESM. However, in the processor contains speculative execution like the boom. The system would try to predict the result of the budget, which could be chosen for most of the time. Then the private information of the inside code block would be loaded into the memory before the examination of the conditional in the budget. So in this attack, the attacker would point to the address space of the victim function and read the victim data in the conditional brand. The conditional brand in the victim function would be run and trained repeatedly. Then, during the attack round, the attacker would give a fail value to the victim that fails the budget in the system. So there will be the cut effect would appear, and the attacker would use the flood and reload technique method to achieve the secret value. The second variant of Spectre is a brand target injection. So in this variant, the attacker target on the brand target buffer to make a mispredict brand target. Because when the program executes, the inherent brand happen and the estimation of the brand is not contained in the instruction itself. So during the runtime, the inherent brand predictor would look up the brand history buffer for the brand history to predict the estimation of the function and immediately start to speculatively execute the function. The attacker could find a program that's similar to the target program to manipulate the indirect brand predictor. Return to the attack scenario. The attack would exploit the jar injection in the RISC V ISA and train it to poison the brand history buffer. And during the attack round, the jar will jump to the victim function instead of the other function, as you can see here. Therefore, the sensitive data could be leaked using the flood and reload technique like in the variant 1. Next part, we will talk about some mitigation methods we have implemented on the RISC processor to defend the program against the Spectre attack. So, since the Spectre has been discovered, there are many research have tried to defend against the Spectre. Most of them are approached by the way to change the hardware configuration of the processor. However, it will be very challenging and hard to work with. So, in this presentation, I will try to implement some straightforward software-based method on the victim program to run it on the RISC V processor to defend against the Spectre attack. So, because this method, the purpose of this method is to modify the victim program to strengthen it against the Spectre. So it requires to recompile the source code of the program, and also it will be effect on the performance of the program when run on the out-order processor. So return to the attack scenario. As you can see here is a conditional brand which normally be exploited on the Spectre variant 1. And now we will modify this conditional brand to strengthen it again, protect against the Spectre attack. There are two approaches we have tried. The first method is insert the friend instruction inside the conditional brand. So it would block the speculative execution. Of course, this would reduce the performance as the program would execute like on in-order processor. So there are no speculative execution. So there will no way the Spectre could exploit the conditional brand. The second method is called speculative load-hardening. We have insert a set of instructions inside the conditional range. And we also use a global periodical state parameter, which will be O1 if a misprediction has occurred, and O0 if one has not. So it will assure that the program would load a safe constant instead of user control data in the case of the miscalculated execution. So that there will no sensitive information could be leaked in the code for the Spectre to exploit. So all of these attack and mitigation have been implemented and run on a RISC V hybrid processor. So in this work, we have designed a hybrid two-core RISC V processor. The system has consisted a dual core of the rocket chip, rocket core, and the Berkeley out-order processor boom. The processor implement has based on the T-boot procedure with crypto accelerator. If you're interested in this subject, there will be a talk from other member of my team at 4 p.m. Thursday about the hardware with the RISC V processor. And the implementation procedure was follow a just execute environment called Keystone and generate using the rocket chip generator and using the IFA config RV64GC. The boom core is a 64-bit 2Y configuration, and the rocket core is also a 64-bit in-order architecture. So before testing the attack and the mitigation scenario on the FPGA, we have also tried to implement the software simulation of the hybrid processor using the validator and the chipset framework with the small boom and the rocket config. And also, we have tried to run the program in the bare metal mode without a Linux OS on an FPGA ZC706. So to communicate between the, as you know, in the FPGA ZC706, there will be an ARM core and the FPGA core. So to run from the ARM core to FPGA core, they have to use interface that can will have to communicate between the ARM core and the FPGA core of the ZC706. So we will run the program on the FPGA processor of the ZC706 without an OS. And finally, we have also implemented the program to run on the OS. The attack scenario run on the OS on the FPGA VC707. So most of the experiment research shows that the Spectre attack has successfully exploited the speculative execution on the hybrid RISC V processor. The attack scenario has frequently success when the rocket was set as the first core and the boom as the second core. But in the opposite situation, mostly there will not any leakage by the attack. This research could be understand that the processor has priority to run the attack scenario on the second core of the processor. Also, by using the dataset command, we have tried to specify the attack to run only on the in-order processor, the rocket core, and the Spectre have failed to achieve the secret information. This could be justified due to the natural characteristics of the rocket core, which does not issue data memory access speculatively and out-order execution. The figure below has described the achieved result if the Spectre successfully exploit the system or not. And in each attacking attempt, would for achieving one character of the private string. And in each attempt, the attack would try some attacking round. Normally, we try 20 rounds and choose the most hit value got from the cut as the result of the obtaining target character. The attack will be success when every attacking attempt got the right character in the private string. As you can see here is a full result when the attacker try to get the full parity. If the attacking success, the obtaining character will be the same as the security, and if not, it will be get nothing. So, to conclude, this work has designed multiple experiments and scenarios to examine the side channel attack via the cut on the RISC V hybrid processor. We have implemented the attack scenario on the software simulation, the parameter program, and on the emote on the Linux to run on the physical FPGA board. The Spectre variant 1, the budget bypass, and the Spectre variant 2, the brain target injection, successfully exploit the out-order core boom in the multi-core hybrid processor. There are some software-based mitigation methods also initially implemented on the RISC V processor to defend against the variant of Spectre attack. However, the approach are required to recompile the program and check off with a significant performance loss. However, it's still a begin for the future improvement method to protect against the such attack on the RISC V processor. This is the end of my presentation. Thank you for listening. And if you have any question, please feel free to ask. Thank you very much.